So it's 2 or 3 minutes afternoon, so good afternoon, everyone. We have a special CFT colloquium today, so we moved it to this big auditorium. And our guest is Jan Arlt. Jan is a good old friend of ours, born German. He did his undergraduate studies in Hanover, then moved to Oxford, got PhD there, returned to Hanover as a postdoc, some junior professor or something, and then got a stable job, final professorship in Aarhus in Denmark, and that's where he is now. The good opportunity for having him here has something to do with our joint paper, which has appeared in PLL about, nearly 2 months ago, and this will be, of course, discussed quite a bit in Jan's talk. So Jan, floor is yours.
Thank you very much for the introduction. It is a pleasure to be here. It has been a pleasure to discuss already this yesterday and this morning, and I look forward to further discussions. In fact, it was a discussion with Kazik in Bad Honnef at the meeting place of the German Physical Society, where we met over breakfast, and I approached him regarding some of the papers I will be mentioning on fluctuations in Bose-Einstein condensate, which really initiated all this collaboration. But let me start at the beginning and introduce you a little bit towards my motivation for the topic. So I will be talking about fluctuations in the quantum gas, which we have recently measured in collaboration with the group here in Warsaw. And I will also tell you how this relates to Schrödinger's work and why this was a puzzle for Schrödinger at the time. But more generally, for the audience that is not working directly with Bose-Einstein condensate, let me motivate a little bit. We live in a time where quantum applications become more and more prominent. We are hoping to build quantum simulators which can answer some quantum questions from systems that we cannot easily access. We are hoping to build a quantum computer or something like it in some years to come. And we are making precision measurements with quantum systems. In fact, all the time you're making those measurements when you use your GPS system. And for all of these purposes, we need some sort of quantum system of which we have good control and which we understand in minute detail. And that's really what we're after. Understanding of a quantum system to a very large extent of detail. And in order to make that point, let me look at precision measurements. Now, man has made precision measurements for many, many years. We are making them every day in terms of measuring where we are using GPS. We are making the most delicate measurements of distances using gravitational wave detectors, as shown here, which have led to the discovery of gravitational waves. And we've been measuring time, starting with sundials, sophisticated clocks, and later atomic clocks to great precision. In fact, we're already using quantum systems when we're measuring time by using atomic clocks. However, we would like to advance these time measurements, or in general precision measurements with quantum systems, to an even larger degree of precision. And how would we do that? Well, we will have to stop using individual atoms as our quantum systems. We will have to build larger quantum systems in which we do not have such simple coherent states as shown here on the Bloch sphere, but we will need some sort of more complicated quantum states. And by engineering these more complicated quantum states, we can first surpass the standard quantum limit, and some experiments with cold atoms have done so, and we can hope to approach the fundamental Heisenberg limit, which is only limited by the measurement process itself. So that's the aim of quantum measurements. And as I said, we will have to go away from using individual atoms. This is supposed to signify a hot gas of atoms, where each atom is really quite individual for itself. And we'll have to go to quantum systems where there is entanglement. And this entanglement is really the more obscure quantum property that is at the heart of many of these quantum applications which we are planning for the future within, for example, the European quantum flagship. Is this really being considered now? And how would one consider such systems for precision measurements? Well, there is work ongoing. I showed 2 experiments here. At Stanford University, a huge system for producing and measuring with Bose-Einstein condensates is being constructed. This is an 8.5 meter and all 10 meter high experiment which launches BECs from the bottom to the top and then makes precision measurements on them. And similarly, there are measurements of gradiometry with Bose-Einstein condensates which are underway at the Australian National University. So measurements with BECs or BECs as the source for quantum measurements is really on the agenda right now, and that is a motivation for us to understand BECs to an even greater level than we have understood them so far. And that's what I want to talk to in the following. So I will talk to you about the BEC production process and its force and challenges. I will then introduce a non-destructive imaging method which we in fact use to circumvent some of the faults that BEC production has today by using feedback stabilized preparation, and that produces extremely precise clouds of atoms which contain the same number and temperature each single time. And only with that prerequisite of having the same number and temperature each single time can we really get to the bottom of understanding Bose-Einstein condensates to a level that we haven't understood before, and that is in order to measure the fluctuations of BECs. So in fact, the deviation from the perfect behavior that one would wish to have in order to make these precision measurements. So let me get started. Now, I probably don't need to introduce this to the largest part of this audience, but when we make BECs, we start from a thermal sample in which the atoms behave quite classical. We lower the temperature, and as we lower the temperature, these wave packets grow. The wave functions start to overlap if you want to use a graphical picture, and in the end, all the particles accumulate in a single ground state, which obviously doesn't have to be a single harmonic oscillator state, but could be composed of many, many states as long as we have a single product wave function. And now we have constructed the large quantum state that we really want in order to make precision measurements, where we do not look at each atom individually, but where we have the chance of producing entanglement and then using that entanglement to make even more more precise measurements than we have made previously. So this is our aim. However, on the way of making this, there are numerous technical but also fundamental challenges, and this fundamental challenge we want to address here. So that's where we want to go, using these quantum systems for precision measurement in the end, or contributing, in effect, to understanding the ultimate limit of these precision measurements. And that limit is going to be set in some way that we have yet to explore by the fact that when we produce Bose-Einstein condensates, we do not only have the condensate itself, but we produce the condensate together with a thermal cloud of atoms. So there are thermal atoms hanging around here. They populate the higher energy states in our trap. And atoms will not only be either in the thermal cloud or in the BEC, but in fact they will move from one to the other. So atoms could leave the BEC, but there would have to be a compensating effect through collisions in the thermal cloud that rearranges the thermal atoms in order to keep the total energy constant. But it would lead to fluctuations between the number of atoms in the BEC and the thermal cloud. So in effect, if I want to make a precision measurement on the BEC, I would have to take this effect into account in some way. So I cannot review this field and the extensive theory that's been done on the field in any comprehensive way. But let me point out a few things. Typically, BEC is treated in the grand canonical ensemble. And we find the transition temperature using the grand canonical ensemble approach. But when we try to extend this and go on to calculate the fluctuations, so here I show the variance of the number of atoms in the BEC, this method starts to fail. At the transition temperature, so this is the temperature divided by the critical temperature, the fluctuations in the BEC explode, they diverge, and that means suddenly the BEC fluctuation, so the number of atoms in the BEC is as large as the BEC. So that means it would be there or not there at the same time, and that makes no sense. And The first one, and this is where the title of the talk emerges, to realize this problem was Schrödinger, who asked himself in the 40s in a number of lectures that Kazik was just explaining to me, how can this be and where does our error emerge? And it took a long time after the 40s in order to treat this problem properly. And I have picked out only one result, which is close to our experiments, and that dates already to 1996, when Hugh Politzer looked at the problem for a non-interacting gas in a harmonic trap. So we are actually quite close to the experimental realization now, where we confine our atoms in a harmonic potential, in our case given by a magnetic potential, and we have very weak interactions. So in that sense, one could hope that the result that he achieved would be appropriate for us. And he said that the variance of the number of atoms in the BEC is related linear to the number of atoms, the total number of atoms, and it depends cubically on this coefficient of the temperature divided by the critical temperature. And I've shown that line here, and the combination of those two lines gives you an idea what may happen. So if you trace out the Pulitzer's result and combine it with the divergence given by the grand canonical ensemble, you have a sort of triangular shape here that may be indicating where we're really going. And in fact, this is confirmed when you make an exact canonical calculation, which was provided to us for our experimental condition by the group here in Warsaw. And that is given by the points. You can, in both cases, ask yourself, what effects will interactions have, which we have to a weak extent in our sample, and that we'll have to treat later. But this is roughly what we are looking at when we think about these fluctuations, which may be the ultimate limit of our precision measurements. So the theoretical understanding, or let's say the fundamental understanding of what was actually going on in those previous calculations was provided from the group here in Warsaw. So a new statistical ensemble was introduced, and that's the Maxwell-Demon ensemble. In this particular case, the Maxwell-Demon has a little bit of a different job than it usually has. Usually the Maxwell-Demon opens and closes a little door here between two ensembles which initially are at the same temperature in such a way that they would acquire different temperatures. And that would break the second law of thermodynamics, and has been the issue of debate for many, many years. The little devil in our ensemble has a slightly different job. His job is to arrange the thermal atoms and the BEC atoms in such a way that they actually preserve energy. So these little guys have slightly different jobs. In fact, this guy fails, whereas this guy succeeds in his job of rearranging the atoms appropriately, and thus provides us with a theory which allows for an explanation of the Pulitzer result, and also for an extension which was done here in Warsaw towards weakly interacting gases. So this was the basis for our collaboration. These papers were in fact the reason why I approached Kazik when we first saw the possibility of realizing such a system in our experiments. So with that, let me continue by looking at the BEC production and both the technical challenges and the solutions that we have introduced in order to realize the fluctuations. How do we make BECs? Well, we have to start with bosonic atoms, which we release into our chamber that is shown here. This is a glass chamber. And then we use 6 laser beams in order to produce a so-called magneto-optical trap. Here the intersection region of these 6 beams is shown in a cartoon. Here you can see the result in real life. So these are glowing rubidium atoms in our chamber which have been collected, typically 1 billion of them, in order to provide a sample that we can turn into a BEC by cooling it further. How do we do that? Well, in our apparatus, we transfer the atoms from the point of collection, which is here, again the 6 beams are indicated, to a region where we can cool them further, and that is done by 2 transfers using mechanical moving magnets that transfer to this region here where further cooling is achieved. How is that done? Well, we use probably about the worst cooling method that you could think of, and that is to remove the hot atoms. So we lose actually a factor of 1,000 of our atoms or so in the cooling process, but it's the only really known way in order to cool atoms. So it's shown in a more theoretical approach on the left here, and it's been shown in practice on the right. So we have made our magnetic field, which is essentially harmonic. You see the different MF states, so the different magnetic states of the atom under investigation, rubidium in our case. And we can use RF radiation in order to flip the spin of these atoms from a trapped to an untrapped state. So atoms at the outside of the cloud will be flipped in their magnetic orientation and thus be propelled into a state that is rejected from the trap. And in that way we can remove atoms. This amounts to cutting the hot atoms out of our distribution, and we achieve a much thinner and therefore colder distribution function. And it's called evaporative cooling because it has some reminiscence, at least, to the way a coffee cup cools when some of the hot atoms evaporate. So this is a known strategy. At the end of such a run, which takes about 2 minutes, we can take an image. We send some resonant light through the sample here, record the image on a camera, and depending on the time of flight, we receive pictures like this one, where we have only condensed a very small fraction in this particular image. You see the very small BEC, which we wanted to obtain here, actually relatively close to the transition temperature, and then a relatively large thermal background gas with which particles will be exchanged. And it's this exchange of particles which we're investigating and which sets then the limits to future precision measurements. And the image that I've shown you before in the introduction and also in the motivation slides was a 3D rendering of this particular image here, which shows the large background and then the small BEC on top in a height profile. Very good. That's the standard way of producing BEC. In a sense, I've told you nothing new here. This is the state of the technology since about the mid-90s when BEC were first produced. And it has a major drawback, because we run this system without any consideration of the particular experimental conditions at that moment. Disturbances to the lab, temperature variations, a tram or a bus passing by. We actually have typical fluctuations of about 10%, both in atom number and temperature, from realization to realization. Some experiments may be a little bit better, some may be a little bit worse. We were about at 10% technical fluctuation. And this, unfortunately, completely excludes the observation of fluctuations between the thermal cloud and the BEC. They're just drowned in these technical fluctuations. So we had to go to new measures in order to make the measurements that we've been looking for. What is that approach? Well, in brief, whenever you have a system that is not controlled, you will see such fluctuations. So you will have to introduce a control loop of some sort. And that control loop will have to take place within that single experimental realization. So it has to, in a sense, produce feedback as the system operates and not only present one result at the end. How would we do that? Well, the first important step would be to provide a measurement throughout the experiment that does not destroy the atomic sample, which is a very, very delicate sample. It is very cold. It contains, at that point, relatively few atoms, and any heating process would destroy it. So the solution to that, and I will go into more detail in a little bit, is to use so-called Faraday imaging, where we use the Faraday effect, that is the rotation of the polarization of light rather than its absorption, in order to produce an atom number or produce an image on a camera from which we can deduct the atom number. And then secondly, we have to devise a fast feedback system which in some way records then this resulting image, computes, in our case on a field programmable gate array, an appropriate feedback, passes that feedback on to some control mechanism, in our case the radio frequency evaporation, and finally produces the appropriate cloud from shot to shot. So this was the technical innovation which really lay the groundwork for the results I'll be showing you. And with that, I can progress to the second part of my talk, which is really the introduction of this Faraday mechanism very briefly, because it's so central to the experiments that we're doing in the end. So, here is Michael Faraday, and he obviously did not discuss this in the quantum world, but in a rather practical world, where he found out that if you have certain media, which have to be transparent, so dielectrics of some sort, and you're sending light through, then the polarization that you send in can be turned depending on the magnetic field strength. And so he could assign a so-called Vedette constant to these materials, which then amounted to giving the rotation amount of rotation for a certain material at a given magnetic field. In the quantum world, the situation is a little bit different. We have so-called spin polarized atoms, so we choose the magnetic quantum state beforehand, in our case by optical pumping. So we know exactly which quantum state we're in, and it's really the interaction of this quantum state with the light that leads to the change of polarization. And that's indicated here. We come in with linear polarization. The atoms are spin polarized. In our case, we send in the light along the magnetic field direction, and the the atomic spin polarization leads to a shift in the polarization direction as indicated here. And obviously that shift will be large if there are many atoms that the light can interact with, and it will be very small if there are no atoms to interact with. So it will be related to the density of the atomic cloud that we are using. And the formula, the resulting formula is shown here. This is the Faraday rotation. There are some pre-constants depending on the material, and then it's directly related to the integral of the density along the line of sight. And that means at high densities we will have large rotation, and at small densities or no densities we will have no rotation. And as thus, this formula shows us that we can produce images from the rotation. Here it's shown in our experiment. We have actually only had to make very little differences to the typical imaging system for Bose-Einstein condensates. Typically, when you have a Bose-Einstein condensate, it sits here, you send some light through, and that is recorded on the camera. In our case, all we did was to add a single beam splitting cube, and that single beam splitting cube rejects all the light that is sent into the imaging system if there is no BEC. So everything is dumped here, in our case, into a photodiode in order to check how much light there was. However, as soon as there is a BEC, that Bose-Einstein condensate, depending on its density, will turn the polarization of the light. And the turned part of the polarization, in our case the horizontal part of that light, will pass through the beam splitting cube and onto the camera. And as thus, produce an image on the camera, which we then record and use as our indicator for the atom number and the density of that cloud. Here the images are shown. So this is a relatively warm cloud. Remember that these clouds can be very, very small when they become extremely cold. So this is a method that cannot be done directly for our Bose-Einstein condensates. Beware of that. It's done for relatively warm thermal clouds for which we can take these images. And here such an image is shown. This is the signal that we actually obtain on the camera. And you can see it's a nice crisp image of cold atoms. We actually also make use of a reference area in which there were no atoms and a baseline average, a baseline region in which there was no light. We can appropriately subtract all of these from each other in order to count how many atoms were in that central region here where we took the image. It turns out, due to the turning of the polarization, there is a sine function involved when we want to recover the intensity from this Faraday signal, and the ultimate image is therefore not related only to the atom number but to atom number and temperature. So from these images, by simply counting, we can extract a quantity that is related to atom number squared and temperature, and in particular the square of the atom number here promises great precision of our technique, and that's what we found out in the following. So here's the atom number extracted, shown for different images taken. So our experiment, as I said, drifts by 10%. So the incoming atom number is not always the same. It starts at different points here. signifying the different experimental realizations. And then we do not only take a single of these Faraday images, but in order to see how precise the method is, we take many of these Faraday images, which are weakly destructive or non-destructive, but they lead to a small loss of atoms. So you can see these decaying curves here. They introduce a small loss of atoms, which is the same for all of them, as we take 100 of these Faraday images. But the important point here, and that's very important for the rest of our work, is that there is very little noise on each individual of these traces. And that means that the Faraday technique is highly precise. It can determine the atom number, not absolutely, so it's not necessarily accurate, but it's highly precise and can determine the atom number very precisely for each of these realizations. And we have shown that. So we have compared the absolute precision that can be achieved with this technique with a noise model, which includes all the different noise sources that are present in our experiment, such as photon shot noise, technical noise, stochastic noise, leading to a combined noise that is shown by this line here as a function of the number of images. So you can now understand this line quite simply. If we only take very few images, then as you have little information, the noise will be rather large. But as you take more and more of these images, the noise will be lower and lower. However, at some point you suffer from the fact that the measuring process itself introduces some noise as it leads to loss of atoms, which comes up here and ultimately limits the precision that you can achieve. So making more than 100 images doesn't make sense. 50 is probably a good number. And we've shown with our experiments, which are shown in blue here, that actually this line can surpass the classical shot noise limit for the given number of atoms that we have. So the technique that we have of Faraday imaging is highly precise, and it's effectively so precise that we can determine the number of atoms in our sample with better than the square root of number of atoms precision. So that's an important prerequisite for any precision measurements that I may want to report. And that's been published in JFISB a little while ago and was really one of the prerequisites. So, given now that we found out there are these, well, on the order of 10% fluctuations in the production process, we now have a highly precise imaging technique which can be applied because it's non-destructive throughout this production process. We may want to implement the feedback process that then leads to highly stable atom numbers at the end. And how do we do that? Here the feedback stabilization is explained. Again, what we do, and I've indicated that before, is we take our Faraday images, we send the signal from the Faraday images to an image processor, in FPGA in our case, and then we modify the cooling sequence appropriately. So rather than just losing atoms using the RF knife that I had indicated before, we can now tailor our RF knife such as to cut a little hole into the distribution, and we cut that hole exactly at the mean temperature of the atoms. And this has the advantage of removing atoms without changing the overall temperature of the ensemble. So this is a method of essentially just throwing atoms away without changing the system properties beyond the atom number. So this is the trick that we use when we run this stabilization sequence. Here it is in more detail. We pre-cool our atoms. So we go from the typical, well, almost 1 billion atoms down to 6 million atoms. And we've achieved at that point a temperature of about 18 microkelvins. So by all means, we're already very, very cold. But 18 microkelvins is warm in our community, as we want to be well below the 1 microkelvin. So we've proceeded to that point without any stabilization. And at that point, we take our first set of Faraday images. As I've indicated before, we become nicely sub-shot noise as soon as we take about 50 images. And that's shown here. So we've taken 50 images of our cloud, and as indicated, we have these 10% fluctuations. So these traces, they come in at different initial atom numbers, depending on the shot that we've taken. Some more, some less. Until that point, it was uncontrolled. Based on that, we can now calculate the loss that we need to indicate, and I will show you in a minute how that is done. And once we have calculated that loss, we can, or the needed loss, we can introduce our loss pulse that removes the appropriate number of atoms, and we can then evaporate a little bit further in order to reach even colder temperatures and atom numbers. And there we take a second set of images, in our case another 100, to check, and you can see that suddenly all these traces have combined into one single trace. So we've achieved the same atom number for all of these traces in this particular set of experiments. And that's really what we wanted. And the question is just, how good have we achieved that? And then obviously at that point we can perform our experiment and perform either the precision measurement that we may want to perform, or the measurement of fluctuations that we've been looking for together with the group here. So just one little explanation of how this this feedback mechanism work. Well, when we take the two sets of images, you can relate them to each other. So here is the number of atoms, essentially the number of atoms at the first measurement. And here is the number of atoms at the second measurement. And if you do not provide any feedback, the correlation between the two is shown in the black dots here. If you have many atoms initially, also after the cooling process, you still have many atoms. That's quite normal. That's what you would expect. However, when you then apply our feedback, that means you follow a gain curve that is given by this formula, which essentially calculates the length of this loss pulse. Then you see that you can be doing better. So that's shown in blue here. So the slope of this line has decreased. That means that for a large variation of incoming atom numbers at the first measurement, the variation of the atom numbers at the second measurement has decreased. And if we then perfect this equation even more by making a second iteration in this evaluation procedure, we can actually achieve the data that is shown in the red line here. That means for a variation of the incoming atom number at first, we see essentially zero variation of the atom number at the second pulse. And that is exactly equivalent in mathematical terms to the picture I've shown you before, where all the traces now fall together and give one single result. How good does this get? Well, again, here we show the total noise budget. The black points indicate the precision of this correlation. So for many different atom numbers at the second imaging point, we get good correlations between the first and the second imaging sequence. And that simply means there are no additional technical noise problems in our experiment. That's all this data says. Now we can turn on our stabilization, and that gives the red data points here, and compare this stabilization with the shot noise limit that one would naively expect. And we can see that, in fact, not only does the precision of the image, the Faraday imaging, and the precision of the correlations surpass the shot noise limit, but in fact also our stabilization itself can yield data points in a window around here of 3 × 10⁶ atoms at the second point, where we can surpass the shot noise limit. That sounds a little bit strange at first. Why can you surpass the shot noise limit in such a classical experiment where you're removing atoms? Well, it's because the real limit of our measurement is given by the number of atoms that we remove. The removed atom number is stochastic, and that sets the real limit of how precise we can get. And we're only removing a small part of our atom number in order to achieve the target atom number. And that's why we can actually be better than shot noise on the atomic atom number. And it's exactly here where our experiments performs best. And it's exactly here where we can precisely determine the atom number and temperature before doing any experiment using this technique. And for details, that was published in 2016 here. And these experiments were the ones that really motivated us to do the fluctuation measurements, because we now knew that we had the perfect sample available, which did not suffer from any technical fluctuations anymore. The 10% fluctuations that I indicated before were gone. And the fluctuation experiment somehow came into reach, and we started to look for the possibility of doing one. So now let me come to the final result, the fluctuation experiments, together with the group here. So, as I said, we start with evaporative cooling. We end with pictures like this one, where we can discern the BEC from the thermal cloud. And typically what one does, an experimentalist, when one realizes the first BEC, is simply to count the atom number in the BEC versus the total atom number. And then, from textbook physics, there are a few simple results that are true for non-interacting BECs, and that is that the atom number in the BEC, shown here on the left, the atom number coefficient of BEC atoms and total atom numbers, versus the critical temperature, or the temperature divided by the critical temperature, grows as 1 minus T over Tc cubed. So that's the curve shown here in the dashed line. That's the sort of textbook result that one finds in statistical physics textbooks. One can become a little bit more refined by including first order corrections due to interactions, which give, well, as you can see here, a shift between 5 and 10%. And one can also do a more sophisticated calculation by including the repulsive effects between the thermal cloud and the BEC. All in all, though, when we try to measure this, you can see that it is still quite noisy, although we had turned on our stabilization technique. So somehow, somewhere out here, just before reaching BEC, the atom number and temperature were extremely well determined. But then, as we do the last evaporation step into the BEC region, the trace gets relatively noisy, and you can see here that the noise is significant and probably doesn't allow us to use to measure the fluctuations. Why is that? Well, there are actually two reasons. The first reason is that we still have technical problems, which I will explain in a little while. They depend on the actual magnetic trap. The second and more significant problem is that it's actually not so difficult to measure the atom number in the BEC or the total atom number, but it's extremely difficult to determine temperatures, because determining temperatures requires fitting to these curves here, fitting to these densities, fitting essentially to the pedestal of this distribution here, and that is extremely difficult and extremely noisy. So the noise is actually not in the relevant quantity on the y-axis here, but the noise is on the x-axis. And both of these problems we had to tackle in order to do the fluctuations measurement. And in order to trace out essentially this curve, which in a way corresponds to the width of the curve I had shown previously, right? So the variance of the BEC atom number corresponds to the width of these data points, right? That's what we're trying to trace out. How large will be the effects of interactions? Well, luckily, theory both from here and we've made a list from various other places. The most recent ones from here, shown in blue and red, and also previous work shown in purple, indicate that the expected variation due to interactions is on the 5 to 10% level. So in that sense, we expect that there is some significant, but they're probably not significant for the first set of measurements. And that was lucky for us, because if they were very large, obviously, if they were very, very large, it would obviously complicate our measurement. So here is the second iteration of how we tag our experiment onto the stabilization technique. What I'd shown you before was the part of the experiment up to here. We evaporate, make the sample cold, we take our first set of images, apply the stabilization, and at this point now in the experiment we have a very, very stable atom number and temperature. And in principle you would say, okay, well then just take your evaporation further and go to the BEC regime and measure there. Unfortunately, we had to do a decompression of the trap. if we evaporate further in the given tight trapping potential we have, we end up with samples that have many other effects present. In particular, a variation of the phase can occur. So we decompress the trap, that's shown here, and we then apply the final evaporation to BEC. And there we take images, as shown before, for which allow us to extract a given number, temperature, and BEC atom number. And we in fact take many of those for a given evaporation endpoint, that is for a given temperature. That's shown here. That we have to do for various temperatures. So in total we recorded 44 sets, which amounted to about 4,000 repetitions of our experiment, indicating a little bit that this was no short experiment to be done on an afternoon, but this required many, many nights of measurements where these traces were taken. Then what do we do? Well, as I indicated before, we count the number first of the BEC. That gives us the parameter N0. We count the number in the thermal cloud. That is shown within the larger circle here. That gives us then, in combination with the BEC number, the total number N. And then we apply our fitting procedure in order to extract temperature from these samples, where we know that this temperature is quite inaccurate and needs refinement. Moreover, we have this problem of the magnetic trap. So our magnetic trap is not entirely stable. It drifts slightly. So when we take these 60 images or so for one certain temperature, the trap varies slightly in depth. And this leads to a slight temperature variation. So if we really want to make a measurement of the fluctuations for one given temperature, that can be a problem. And I show you how we solve that problem. Here that slight variation is shown. How can we circumvent this? Well, when we actually do the evaporative cooling, right, we remove atoms, and you can see here if the trap bottom varied slightly, then depending on the endpoint of this RF knife, which removes atoms, we may have both more atoms and a warmer temperature at the same time, or if the trap bottom was closer, further up, we would at the same time have less atoms and lower temperature. So there are three quantities here which are closely correlated, and that is the total atom number, the atom number in the BEC, and the temperature. How can that be understood? Well, let's say we've done our preparation well. We have a very, very small distribution of number and temperature after our stabilization. As we then evaporate and have these small variations of the trap bottom, then larger atom numbers will correspond to larger temperatures and smaller atom numbers will correspond to smaller temperatures. We would have correlations between them in this particular fashion. And that would be independent for each of these measurements. Whenever we have stabilized, we would get these ellipses of correlation. And that's exactly what we see. As we make our Bose-Einstein condensates, we see that they're quite strongly correlated. So we can access a small atom number window between 2.3 and 2.5 10 to the 5 atoms, and that will correspond to a very narrow temperature window. As I show here, watch the axis. This is between 138 and 146 nanokelvin. So we are distinguishing something on the order of 8 nanokelvin here. So it's really a tiny window of temperature we are accessing in which we are measuring the fluctuations. And the fluctuations are then not the total fluctuations, but they are the fluctuations with respect to this correlation line. So we calculate the fluctuations by taking the difference between the temperature, the fitted line here, and the data points. And the same is true for the BEC. So N0 is shown here. This is the BEC atom number. And it's in fact correlated the other way around, in the sense that if we are colder, we have larger BEC atom number, and when we have more atoms and we are warmer, we have less BEC atom number. And again, we can calculate the variance by taking the difference with this line. So let me first show you our result for the temperature. Initially, the temperature data indicated this behavior of the BEC atom number versus T over Tc. But then we can exchange for a given data point, and let me show that again. For this given data point, we can exchange the measured temperature, which was this one, with the one that we would extract from the correlation data. So now we do not take the individual data points temperature, but we use the overall information that we have on this entire data set to use the correlation to reach this temperature. And when we do that, you can see that the data quality drastically improves. And we are now reaching a level between a level of the atom number, BEC atom number, that may help, that may allow us to actually measure the variance of this curve. And this is really the decisive point. Both the stabilization is necessary in order to access such a narrow temperature window, and the correlation technique is required in order to make this variance so low that we can actually measure the fluctuations. Here the final extraction is shown. We actually don't use the temperature, that's only an additional benefit of our measurements. We extract the variance directly from the data that we obtain in the correlation between the BEC atom number and the total atom number. So we calculate the variance from this graph, and when we do that, we obtain the following data set. At first, you notice that there is a drastic increase somewhere in the vicinity of the critical temperature. So here the variance of the atom number is shown as a function of T over Tc. And now we can compare to theory. And first, we compare to the exact result computed here in Warsaw for our experimental conditions. And we notice that the overall shape fits well, but there is a small offset. And that small offset is in fact expected. It's the offset due to interactions, which I had indicated is between 3 and 5% somewhere. So we can make a fit, and we use the formulas that I had introduced in the very beginning, the grand canonical on the one side and the non-interacting Pulitzer result on the other, in order to make an empirical fit function, which is shown in orange here with an error bar. And we see exactly that we get a 4.5% difference in temperature, which is the expected result for an interacting sample. So we have very good indication that this actually is now a measurement of the fluctuations precisely as expected and measured for the first time. And it also shows us that the peak fluctuations are not far from the expected value, and that means that interaction in our sample still play a minor role. So in the future, we actually want to resolve these interactions precisely. We would also like to know what the distribution function of this atom number distribution is in more detail, and there is much more work to come, hopefully in collaboration with the group here. And as I said, the indicated effect of interactions was relatively minor. And with that, we've really put a brick in a somewhat older puzzle, started in the 40s by Schrödinger, later continued by Uhlenbeck in the 70s, then picked up here in the 90s, and finally measured by us in the 2010s. And with that, we hope to contribute to future precision experiments on BEC using BECs, determining the ultimate limit that these can arrive at for a certain temperature. And these were the two typical, or the two ongoing BEC experiments that I indicated before. And with that, I've reached the end of my talk, and I hope I have indicated to you how this collaboration has very fruitfully led to the observation of these fluctuations. These were the experimentalists involved. Mirek Gajdac and Andrew Hilliard were the first team that worked towards the stabilization. The current team are Mick Christensen and Mikkel Christensen, who are working on the experiment. We have two collaborators, two senior collaborators who've contributed their ideas to the experimental realization, and we obviously have the theory group to collaborate with here in Warsaw. Thank you very much for your attention.
Thank you very much, Jan. I think we could appreciate the fact that their work in Denmark was harder than ours in Warsaw. We have time for questions. Yeah, okay. Krzysztof will help with the mic.
Could one imagine doing this without stabilization, but just with post-processing, like this atom number fluctuation? I mean, if you have like a especially if you have a faster experiment with 10 or so cycle?
Yes, you could. If you the overhead of data that you would have to take is rather large. It would also be difficult to use this correlation technique. There are some issues involved in actually determine the correlation that we have, well, in this data here, if you don't have the stabilization running. But in principle, yes, it's not excluded. Not with our experiment, though.
Okay, more questions?
Oh, thank you. You showed some very nice curves. If you go to the next slide, this last curve that you have, which has two colors. Yes, this one. I have a question. How do you define the error bars on temperature in this case, in these points there?
So these temperature error bars, they actually cover the whole temperature interval that we're working in. So, you know, as I showed here, the data, the individual temperatures measured for each of these data points then covered this 138 to 146 nanokelvin area, and we simply put the error bar as the whole area. But we use in order to then place an individual point, we just use the mean of those, right? So in the sense, this beautiful information here, which leads to this very thin data plot, is not used in our final result. It's a byproduct.
Okay, more questions?
Jan, in the microcanonical description that we used here in Warsaw, the control parameters is number of particles and energy. And we know that temperature is just the response, and it fluctuates in this microcanonical ensemble. Is it much more... Okay, I don't know if it is possible to measure the energy after time of flight, and maybe instead of using temperature to plot these fluctuations as the function of energy. Will it be more noisy?
I don't know of any other way of measuring energy.
After expansion, if you assume that everything goes into kinetic energy, then you might having time of.
But that's exactly what we measure when we measure temperature. Ultimately, right? We measure the velocity
but then
distribution.
You feed, and this feeding is really very, very noisy. We know it from our first attempts with classical fields that we produced this beautiful distribution of thermal cloud and peak of condensate on the top, and then we had a problem because we controlled the energy, what is a temperature, try to fit. And Krzysztof Góral, who was just doing these calculations, refused because he said, I can get any temperature you wish. I don't know how they do it in experiment. However, if you have distances there, and if you just assume that this distance is due to the momentum times, you might have energy. Will be the same level of inaccuracy, or
yes. I mean, you could rather than sort of extracting temperature from the fit, you could sort of fit the sort of count and use the distribution function somehow, right? So use this distance here in order to extract the energy directly from the velocity distribution, and this could be, whether it would be better, I don't know. We haven't tried, but it would be a nice attempt to make, because it would avoid the fitting, which we know is noisy and not very good. It is, however...
Our prediction shows that the microcanonical fluctuations, namely the ones that are, governed by the constant energy, are lower than that of the canonical ensemble.
Mm-hmm.
Wow, okay.
It would be nice to... I mean, so far, we were always operating in the regime where I was under the impression that the microcanonical and the canonical result are very close in theory.
Well, for the idea, because they are never completely close. It's really, they are clearly distinct.
The same scaling with n and temperature.
Yeah.
Yes, but we should.
The slope is different.
Yes, we should investigate that for the non-interacting regime, because we are not so far from it. And if the effect is larger, if we can find a sort of sweet spot where the difference between canonical and microcanonical is larger than the effect due to interactions, then we should measure it, right?
So
because then we can actually find out.
Yes. So one point of refinement, even though Mariusz correctly says that the energy is really correct control parameter for the microcanonical ensemble, the way we were always plotting these things were versus the microcanonical temperature. That's the one that fluctuates, right? So we are not using, well, we are claiming that energy is the right variable, but then for the benefit of the experimenters, we were always translating it into microcanonical temperature. But one can stay with energy and one can do similar calculations, parameterizing the results with the energy, and that could be maybe directly compared.
That would be very nice to do.
Yes.
Yes, I mean, we can definitely sort of either use a different technique of obtaining energy directly from the velocity distribution, or just replot in terms of energy, and then it would be nice to compare with microcanonical versus canonical.
Yes.
Great.
Good point, thanks. More questions, remarks, criticism. Nice words about this word.
Piotr is up there. It's again the fitting mechanism. So what we did, and this is so what we do out here, you see that we have data points for the variance of the BEC atom number in regions where there is no BEC, right? So you would say that, well, these 4 data points here, they're actually quite paradoxical. And all we do there is that we take the exact same evaluation mechanism and we run it on data where there is no BEC. So we fit the thermal cloud, we subtract the thermal cloud from our images. We get essentially a flat background. Then on that flat background, we try to count how many BEC atoms are there. On average, that is 0, but only on average. Sometimes we count a few. Sometimes, in fact, we can get negative counts of the BEC in that particular scenario because it is just noise that we're counting. And that noise, or the variance of that noise, then results into these 4 data points here. And we assign that as our noise floor. So it's just applying the evaluation technique for the variance of the BEC to data sets where there is no BEC. Yeah, it's sort of essentially, once you have, if we look at an image, right, let me go back to one. It's, where's one? So you don't have this little lump in the center. You subtract the distribution that leads to the blue or dark blue thermal cloud here, and then you remain with something that looks a little bit like the white noise out here. So this is the remaining photonic, this is dominated actually by photonic shot noise. And that will also from shot to shot vary a little bit within this little region in the center here.
Yet another question. If not, then before we thank Jan again, let me tell you or remind you that outside there will be tea and coffee and maybe some cookies. And this is a good opportunity to ask other questions and talk to Jan before he's gone. He's flying back this afternoon. So.
But there is a little bit of time for discussion.
Absolutely, yes. So let's thank Jan again.
Thank you.